So this also may have equations like BJT for the current and voltage, etc.
That is true. Shall we write that down? We will take the example of the NMOS.
So that we can start building the circuits.
We need to start, right? We'll do that. So I'll write the BJT equation for reference. Then we will look at the MOSFET.
Yeah.
Because now that the students know the BJT, they will be able to understand, where the equations come from. So in the case of the BJT, let's say beta is very large. What we said was the emitter current and the collector current, whatever you want to look at it, whichever way you want to look at it, depended on some saturation current IE naught times e power VBE
by VT
minus 1. Right?
Yes.
This was the equation.
Yes.
When VBE was very large compared to VT, we neglected the 1 and so on. Almost looks like an exponential curve.
Correct.
Right? So the base emitter junction voltage decided
the current.
Right? Same way for the MOSFET, the gate source voltage is going to decide the drain current.
Okay.
Right? Which is also the source current. So
ID. So it's almost similar.
It's almost very similar, except the relationship is not exponential.
Okay.
Right? There was one more thing we said, no? We also said the collector base junction should be reverse biased.
Yeah.
Right? So collector base emitter. So NPN. So we said this PN junction is forward biased, but this junction should be reverse biased. Right? Same way, for normal, if you're trying to build an amplifier, you want the drain voltage to be much larger than the gate voltage. Right? The exact equation is different because it's not a junction, but there are two regions of operation. Right? So we will look at that case. So we'll look at something like this. In fact, I am writing it here.
D and drain.
Gate and source.
Yeah.
Okay. In fact, what I am going to do, I am going to write down the exact requirement for what you want for the equation. So here we had exponential. Now your gate current is always 0 here. Whereas here the base current we said was IE by beta plus 1.
Yeah.
Right? Beta is very large, it is very small. But here the gate current is always 0. The drain current actually can have 3 types of relationships with the voltages.
Oh.
Okay? First of all, remember this is an exponential relationship.
Yeah.
So we saw it's like a diode, no?
Correct.
Until you hit some 0.6, 0.7 volts, very low, right? It is some small conduction, we sometimes very often neglect it also. It's almost like a knee point where it increases. Same way, the MOSFET also has a voltage till which it will not conduct. In fact, the MOSFET is better. The classical MOSFET has 0 conduction.
Till VGS.
Till some voltage. Till VGS goes to some voltage. We will call that voltage the threshold voltage. And in this case, we use small VT, V subscript small t, no? We will either use V subscript capital T. Or V subscript, some textbooks use capital TH.
Maybe
right?
TH
so, maybe to, if we don't want the students to be confused.
Yeah.
Right? So, what we will say, if VGS is greater than, some textbooks use like this, okay, I'll just say, or some textbooks use like this, it's called the threshold voltage.
Okay. So the gate opens only after that.
Correct. This is the threshold voltage of the MOSFET.
Only then the ID starts flowing.
Only then ID starts flowing. So in fact, we'll write it like this. if VGS is less than this threshold voltage,
ID will be 0.
ID will be 0. Right?
Hmm.
So that means until you apply gate to source voltage of some value, the device will not even conduct. Right? Then
After VT?
after VT, the device can start conducting. Again, there are two regions. We will write down both regions. If which one do you want to use, VT or
VT,
VTH?
VT.
VT is okay,
Yeah.
no? V capital T.
Capital T.
We'll just use that.
Yeah.
That is more commonly used.
Yes.
So if VGS is greater than VT, then there are two options depending on this VD and VG. Okay. It turns out instead of exponential, the device is quadratic.
Oh.
Okay. So we will now this is going to become an equation with several parameters. We'll explain one by one. So
Mu n
half
C ox.
mu n C ox W over L into VGS minus VT the whole square.
VT also okay.
VT we know.
VGS okay.
Yes.
But other things are not known.
Other things we are not known, right? So we will define each and every one of them.
Okay.
Right? So, well, let me write the condition. If VGS
is greater than VT.
is greater than VT, that we have written here.
Correct.
We'll write it like this. And we have to say VDS is greater than VGS minus VT. Okay. If these two conditions are satisfied, the current will have this equation.
So drain to source voltage.
The drain to source voltage should be greater than the gate to source voltage minus VT.
Okay.
Okay. And this VGS minus VT is a very useful quantity. Some people call it the overdrive voltage because threshold voltage is when the device starts conducting. So then whatever voltage you apply on top of it is the overdrive.
Yeah.
Some people like to call it VD sat. We will see why in a few minutes. Textbooks, we just need to tell the students because the textbooks will have different names for it.
I think VD sat is common.
VD sat is common. Correct. Okay. So now we need to, very important, no? We need to explain what these things are.
Yeah.
So this mu n is the mobility of electrons. Some device property. Actually, from the circuit point of view, we don't need to maybe spend too much time understanding. If the students choose to take a devices course, they will understand what this is, how it depends on the device parameters, etc. We will just assume that.
Anyway, for a device, it is fixed.
Correct. For a device, it is fixed.
So all this mu and C ox W by L put together, I can give one value.
You can give one value. Now, there may be integrated circuits where you can change W and L.
Understood.
But typically not. Like in BSCS, if you have an electronics lab, we will give them a MOSFET. That will already have, everything will be fixed. VT will be fixed. W, L, mu and C, all of these will be fixed.
So if you are designing and fabricating, then you can choose.
Then you can choose. Correct.
Understood.
If you go to the market and buy a MOSFET, everything is fixed, right?
Understood.
So this is the mobility
of
electrons.
So the holes will have some other name.
Holes will have some other name. So on the next page, we will write down the equations for the pMOS also. They are slightly different, just like the P and P had a slightly different equation. Okay. C ox is the oxide capacitance per unit area.
Oh, so you mentioned that there is some insulator.
Yes, correct.
So it comes from.
It comes from that, and it is basically some, let us say, femtofarads, nanofarads per micron squared normally. I mean, in modern MOSFETs, which are normally very small, maybe femtofarads, tens of femtofarads, hundreds of femtofarads per micron squared. So it is capacitance per unit area. That is what we want to say. So
Femto means 10 power
minus 15. Correct.
So very small value.
Very small value. We'll just write it like this. Capacitance per unit area. Why unnecessarily tied to femto and micron? Correct. Right? Because you can go to the market and buy a power MOSFET which will be millimeters,
Correct.
right, wide.
So W and L are some width and length.
Width and length of the device.
Or the channel in which the current is flowing.
Channel, correct. So the L is the length of the channel, width is the width of the device.
Yeah. Half is anyway half.
Half is just half, correct. That comes out from the device characteristic. And Vt is the threshold voltage, we already know that.
Yeah.
So now we have defined, I think, everything with respect to this equation.
What if VDS is not greater than VGS minus VT?
So that is like in the NPN, if we push the device such that the collector base junction is reverse biased. So we know that the device will not work properly. In that case, we drew the curve, we said, it is, if VCB is reverse biased,
Then
we said that it is in the forward active region.
Correct.
And we said that if VCB is forward biased, we said it will go into the saturation region. Unfortunately, devices engineers decided to confuse us. In the MOSFET, this region is called saturation.
So, but it's not that kind of saturation.
It is not that kind of saturation. It is a different saturation. But the word used is the same. The reason, there is a very specific reason why the word is used, right? And we will discuss that. Once we draw the curves, we will understand why it is called saturation. But that is very important to realize. This is the saturation. So if you put these two conditions together,
looks like the current is not changing with respect to
exactly
VDS.
with respect to VDS. So it is, we say that it is saturation. That is correct. So this is the saturation region of operation of the MOSFET. Now we will do the other one, which is the other two conditions, no?
Yeah.
So we don't need this. So we want the fourth condition, no?
Correct.
Sorry, the third condition. So now VGS is still greater than VT, but VDS is less than VGS minus VT.
Basically, VDS is a small voltage.
VDS is a small voltage. So if you had the drain voltage much larger than the gate voltage, that is what this is saying.
Correct.
The source voltage is common to both sides.
Yeah.
Right? You can also, by the way, some textbooks also write VD minus VS greater than VG minus VS minus VT. Right? You can cut off VS on both sides. You can say that the drain voltage is greater than the gate voltage minus VT. You can express it in that form also. So some textbooks also use that.
Okay.
So the drain voltage is much larger than the gate voltage. Right? Then it is, that's why I wrote it like that, not VDS. I just wrote it like that.
Yeah.
To compare it to the bipolar.
So for the next case, that condition VD very, very greater than VG
is not satisfied. Correct. So we will most likely less than, much smaller than VG. So the border region is this, VG minus VT. You can also express it like this, just like before.
So for this region, there is a different expression.
There is a different expression. That is also quadratic, but slightly different expression. As you rightly pointed out, this is called saturation region because the current doesn't depend on VDS.
Yeah, because I did not see VDS in the equation.
Correct. Now in the other region, it will start depending on VGS.
Okay. Yes.
So in this region, the drain current, same set of parameters, mu n C ox W over L.
That half is gone.
Half is gone.
Okay.
Correct. and this thing starts having a dependence on VDS. So VGS minus VT times VDS minus VDS squared by 2.
Okay.
So in fact, if you set VDS equal to VGS minus VT, you will get the same expression. It is a continuous curve. It is, the MOSFET operation is not discontinuous, luckily for us.
Okay.
So if you set VDS equal to VGS minus VT, you will get half into VGS minus VT the whole square.
So for a fixed VGS, if I change VDS,
Yes.
current will change.
Current will change.
Like a resistor also.
Almost like a resistor. Correct. This is like a nonlinear resistor.
Correct.
Right?
Because there is a VDS square also.
VDS squared also. But you can make it look very close if you make VDS very small.
The
Right?
square term will
Square term will become much smaller. Then it will look like a good resistor. And because of that, as you rightly pointed out, so this region is called the linear region. And there is one more name.
Triode.
Triode. I don't know why. Do you know why it
I
came?
don't know.
There must have been just like you have a diode, you also have a device called a triode.
Triode.
And I think the IV characteristics looks like a triode. I think that is why they also call it the triode region.
Okay.
This is what one of my teachers told me a long time ago. That
We'll convey the same thing to
we'll convey the same thing to the students. So in the linear or triode region, there is a dependence on VDS. That is the big difference.
So as an amplifier, you may not choose this region.
Yes, we don't want to choose this.
Because you cannot easily control the current.
Correct.
Load itself, I mean, if I connect a different load, then I have a different current.
You have a different current.
Yeah, it's
correct. In fact, you can see your BJT equation does not depend on VCE. That is what you use to build the amplifier.
Correct.
So it looks like we should be using the saturation region. Correct. We'll use the saturation region.
Okay. Irrespective of regions, the IG, yes, or
Luckily,
the gate current is
gate current is zero.
0.
Irrespective of whatever happens. That's the good part. So that's what we started with, no? You wanted
No current.
a device with beta.
Correct.
Infinity.
Correct.
No base current. Correct. Okay. Great. One last thing, I think. The IV characteristics.
How it looks like. Although we have equations, good to have some.
Good to have some
plots.
idea, no?
Yeah.
Plots. So what we'll do, before we go to the IV characteristic, I will just write maybe just the saturation equation alone for the pMOS transistor. Then we'll go to the IV characteristics of the NMOS.
Correct.
Once we write for the saturation, the students can
Write it for
triode, compare it with the textbook. So gate, source, drain, and we again have the drain current. Here also IG is 0, so this is a pMOS, and IG is 0 here also, no problem. And if, what did we say here, VGS is greater than VT, we will say the same thing, except it is the source to gate voltage.
Okay.
Just like you had VBE for the NPN transistor, and for the PNP you said emitter base voltage.
Correct.
Same way, the source to gate voltage should be larger than some threshold voltage, right? And now we have to be careful, we'll call it VTP. If you're using a pMOS, it will have a different threshold voltage. So the pMOS is a completely different device, right? Just like an NPN and a PNP are completely different devices. Just like that, pMOS and an NMOS are completely different devices. They will have different device characteristics also.
BJT, but equations were same.
Equations are the same. Here equations, as long as you change BE to EB, the equations stay the same. Same way here, if you change VGS to VSG, right?
Yeah.
Same way, if you change VDS to VSD, you can see some similarity between the equations.
Yeah. But here this mu.
That and all will change slightly.
Yeah,
Correct.
yeah.
So the mu will change. Absolutely correct. So the condition is VSG should be greater than VTP.
Yeah.
And so basically what this means is that the source terminal is at a higher potential compared to the gate terminal. Now, some textbooks, we have to warn the students, some textbooks will use things like mod VTP because they will think of VT as being negative and so on. We probably don't want to confuse them in our course. We will assume that VTP is positive and the source is at a higher potential compared to the gate. We will write it like that.
Yes.
Now, current is flowing from source to drain.
Yeah.
Which means, like I said, just like this was higher, the source to drain potential should also be very high.
Correct.
Instead of VD, right? So the condition we want is that VD should be much smaller than VG for operating properly. So exactly reverse.
Understood.
So I'll write it here.
Yeah.
VD much smaller than VG is the normal amplifier operating region. In this case, we will say, write it like this, the drain voltage. So here in the case of the NMOS transistor, the drain voltage could go as low as VG minus VT.
Yeah.
So here the drain voltage can go as high as, should be less than VG plus VT.
Okay.
That is the difference. So a slight difference here.
Okay.
Or VDS is less than VGS plus VTP. So you wanted drain voltage to be very small. If you start increasing the drain voltage, it will move away from saturation closer and closer to the linear region until if it goes more than one threshold voltage above the gate.
Okay.
So that means that VDS, VSD becomes very small. Then it goes to the linear region. We want to avoid that.
Okay.
So we'll apply these two conditions. Then ID will be, half will still be there. Instead of mu n, what will we have?
Mu
P. Must be P, no? We had an NMOS mu n. pMOS will use mu P.
Okay. So
Cox,
this is the mobility of
holes. Correct. And W and L are the width and length of the pMOS transistor. Cox is the oxide per unit capacitance per unit area of the pMOS transistor into VSG minus VTP the whole square. And this is the mobility of holes. P-type charge carriers.
So it's almost same.
It's almost the same, correct? So in most practical cases, once you learn this small
Threshold
difference,
voltage trick. Yeah.
correct, it is almost the same. The equation doesn't change.